geometrical designs of aortic valve can we predict durability? Questions so far?
Cancel. Thanks. Okay, so the framework for today's discussion on durability is going to be the following. First, we'll discuss the device system and the responsible people, the engineers. Then we'll look at the patient selection and the procedure, where you have the physicians who are who are responsible. And then we have the device-patient interface, which requires an understanding between the engineer and physician collaboration. And each of these points, through device system, patient, procedure, and device-patient interface, we have to be able to detect the hazards and failure modes through design verification and design validation. This was a book that I came across while preparing for this talk, and it says the following. It recounts examples of how various medical devices failed and caused severe injury and death. While some of those failures resulted from bad engineering, others were simply incidents that resulted from inadequate knowledge of the environment in which these medical devices were meant to function. If one does not know the full range of insult to which a medical device would be exposed, it is impossible to design for it, and this is why we have to understand the device-patient interface. The device system is composed of the delivery catheter system, the loading system, and the bioprosthetic heart valve with the support structure, leaflets, and sealing skirt. And at each of these stages, we need to understand the design geometry, the material selection, characterization, and material manufacturing and processing. And there is great relationship between each of these levels between the rows and the columns. Now, if we look at the design landscape for a moment, with the Edwards, the core valve, the direct flow, the heart leaflet, and the Sadra, we notice that the support structure can be stainless steel, nitinol, or Dacron. The leaflets, bovine or porcine pericardium. The Edwards Sapien has anti-calcification treatment, as does the direct flow. And the sealing skirts are all different. Polyethylene terephthalate, porcine pericardium, polyester, braided polyester, and polyurethane. Furthermore, the deployment mechanisms are balloon expandable, self-expandable, and inflatable. The device profiles range from 16 to 24. The 3 R's mean recapturable, repositionable, and retrievable. And the newer generation devices have these features. And these valves come in a certain number of valve sizes, and it's unlikely that one valve size will fit all. So some preschool mechanics before we move on. So we have stress and strain. Stress, by definition, is the force per area, and it's given by this ratio, force over area. And the units are pascals or newtons per meter squared. Strain is the deformation of a material due to the stress. And the best example I can give you is possibly my wife, who causes a lot of stress and causes me to strain quite a bit. But the definition of strain is a change in material length over the initial length of the material. And this strain is unitless, and there's a relationship between stress and strain, which is called Young's modulus. And Young's modulus is a characteristic of a material, and it's the material deformation that is proportional to the imposed loads, and each material has a Young's modulus, and it's described by the stress over the strain. So one of the design challenges of transcatheter aortic valves is going to a lower profile device. And we can make the analogy with the car industry, where you have a truck design going down to a smart car. And some of the considerations are going to be a change in materials and design. There's going to be altered driving terrains for these vehicles, and therefore they're going to be subjected to terrain-specific testing conditions. They're going to have different safety features, and you can imagine that with the smart car, you're going to have greater maneuverability. Similarly, going from a large French to a smaller French size, you may have a reduction in the number of struts and the number of stitches, and also in the number of material thickness. And all of these may, that is important, may lead to a decrease in structural redundancy. It may lead to a decrease in radial force, increased stress on the loaded material by the definition, and we may question whether or not there's going to be an impact on durability. So what were some of the evolutionary changes that led to a lower profile core valve device? The first generation was 25 French. It was self-expanding and it had bovine pericardium. When they moved over to the second generation, it was a porcine pericardium, and this was the reason why they went to a 21 French delivery catheter system. The porcine pericardium is thinner than bovine pericardium. They then followed that by the third generation, where the skirt and the leaflets were cut into 3 independent sections, and this allowed them to choose more specific material. And this led to their 18 French delivery catheter system. If we look at the evolutionary changes of the Edwards device, the Cribby Edwards was a 22 and 24 French delivery catheter, stainless steel stent with untreated equine pericardium. The Edwards Sapien had a bovine pericardium, which is now thermofixed for anti-calcification. There was lengthening of the skirt, and the device remained at 22 and 24 French. But recently, with the introduction of the Sapien XT valve, this is now made of a cobalt alloy stent. There is a change in the frame design, more open cell frame, reduced number of struts. You have a different geometry in the leaflets, a scalloped leaflet geometry. There's also, not to go into details, but a change in the way the device is loaded on the delivery catheter, and some of these changes has led to a decrease in the delivery catheter size. So how can we assess valve durability? You can look at the preclinical and clinical stages. The preclinical, we have the in vitro bench testing and the in vivo animal testing. The in vitro bench testing that we'll go into a little bit more detail has hydrodynamic testing, durability testing, and fatigue testing. And at the moment, we have inadequate animal models that simulate in vivo conditions. The proof in the pudding is going to be in the clinical in vivo human experience, and this is where our answer is going to be in terms of durability. And we have to understand the device-patient interface that we had mentioned previously at both the acute, intermediate, and long-term times. So what are the in vitro testings that we just described? We have the hydrodynamics, which provides indicators of valve performance and fluid mechanics, and typically gives us pressure gradients, the regurgitant volumes, and the effective orifice areas. Then we can look at durability testing, and that assesses the wear characteristics of the leaflets. So that's specifically looking at the leaflets. And the test is usually run at 200 million cycles, which represents approximately 5 years. And the machine is run at 20 cycles per second. With respect to fatigue testing, this assesses the structural integrity of the support structure. And this is run at 600 million cycles, which represents 15 years. And the tester is run at 40 to 80 cycles per second. So what are the challenges to these in vitro testings? For the durability testing, for the fatigue testing, the most important thing and one of the take-home messages is that we need to simulate the in vivo conditions. And therefore, we need to understand the loading conditions. And the loading conditions may be understood through the patient characteristics. What are the ranges in blood pressure that these valves would be exposed to? What is the compliance of the aorta in these elderly patients? What are the mechanical loading features, the radial, torsional, and bending strengths imposed on the valve? What are the out-of-round configurations that we'll see with these valves? And how are these valves going to be aligned, and therefore how are the velocity profiles going to change? And importantly, we're going to have to understand the biological response over time and whether or not there's a change from post-implant to 1-year follow-up in the mechanical loading features. And therefore, we're going to have to understand how the device impacts the patient, but also how the patient impacts the device. So with respect to hydrodynamic testing, this is a pulse duplicator. It produces pressure and flow waveforms that approximate physiological conditions. You can create pressure differences at various cardiac outputs between 2 and 7 liters per minute at single heart rates. And you can calculate regurgitant volumes, closing and leakage, at different mean back pressures at varying heart rates. And you can also study velocity flow fields and shear stress flow fields. So these are various valves put in pulse duplicators. You have the Edwards device on the top left. You have the heart leaflet technology on the top right. And the Medtronic core valve is not functioning. Okay, we move on. So that's how the valve would be functioning in a pulse duplicator. So when we look at durability, this is something different now. We talked about hydrodynamics, but now we talk about durability, and this is done in an accelerated wear tester. And it creates high rate cycling, and the test parameters of this machine are determined by the device design, by the material selection, and the anticipated failure modes. And the target peak pressures across the closed valves should be maintained for greater than 95% of all test cycles. These valves are then functionally evaluated at regular intervals, weekly or every 20 million cycles. These valves are actually removed from the accelerated wear tester, they're inspected, and then put back into the pulse duplicators, where you can assess pressure gradients, where you can assess closing volumes and leakage volumes against a control valve that is a surgical valve at this time. So we now move to fatigue testing. And as we said, the loading conditions are important not only for the durability testing, but also fatigue testing. And these loading conditions, once you understand them, are then put into a finite element analysis model, a computer model. And this will allow us to understand where is the maximal stress and strain on the device. These loading conditions are also imputed in the component fatigue tester. And you then test the device to success at 600 million cycles, or you test the device to failure. And whether it be 200, 300, 600, 700, or 800 million cycles, when it fails, you may understand how these valves may fail in vivo. So there's another important part to this equation, and that has to do with material fatigue characterization. And that is, what are the characteristics of the materials that are included in these valves? And the way you characterize materials is through an SN curve, a stress, strain, and cycles to failure. And let's look at this in a little bit more detail. On the x-axis, you have life cycles, 100, 200, 300, 600 million cycles. On the y-axis, you have strain. You can also have stress or strain. And this is the SN curve. That is the stress and the cycle number at which the material will fail. Therefore, if your stress is above this line, then the material is likely to fail. If the stress is below this line, then the material is less likely to fail. Now you've put your loading conditions into the finite element analysis, and you've understood what are your maximal strains and stresses. Now you were interested approximately at the 600 million mark. So suppose now that your finite element analysis tells you that the peak strain was somewhere here. That's the maximal stress. Well, then you're going to think, I'm in trouble. The material is likely to fail. But if your finite element analysis tells you that the peak strain is somewhere below the SN curve, then you have an FOS, or a factor of safety. And this factor of safety by the FDA is a factor of 2.
Niccolo, sorry to interrupt you, but looking at the time, we have 20 minutes left and still 2 more presentations to come. So perhaps I'm not sure how long your presentation is left, but perhaps...
probably about another 5-10 minutes.
Perhaps you could reduce the... Okay.
So after you understand the device system, then we have to understand the patient and the procedure. And for terms of patient selection, it can influence the patient, the prosthesis size selection, the delivery of the device, the positioning of the device, the deployment of the device, also the alignment of the device, and the post-deployment shape of the device. So we already spoke about the aortic valve annulus measurements and what are the shortcomings in 2D and in 3D, where we can have a minimum maximum diameter. And we have to understand how to use these valve measurement sizes in order to select the patient prosthesis, and this may affect valve function and the post-deployment shape of the device. So now we move to the procedure, and we're just going to go run through a few questions and for us to think about possibly in a discussion. Will valve crimping or loading influence valve durability? And this is an on-label practice, theoretically has been tested by the companies. Will post-implant dilatation influence valve durability? This is an off-label practice. and to the best of our knowledge, has not been tested by the companies. Will valve and valve implantation influence valve durability? This is an off-label practice. Will sequential valve implantation influence valve durability? That is 2 valves in series. Will a transcatheter aortic valve and a surgical aortic valve, a TAV and SAV, influence valve durability? On the left side, we have a core valve and a mitral flow. On the right side, we have a sapien and a paramount performed by Professor Walter at Leipzig. And so there's a number of questions at different aspects of the procedure where we can ask ourselves, is that practice going to impact on durability? And then there's the device-patient interface. And this is important to understand the loading conditions so that we can properly design for the aortic valves. And we already discussed some of the loading condition parameters. This is a study looking at the circularity index with the Edwards, also the geometry and apposition of the core valve with multi-slice CT. And we can understand that in not all cases do we have a round configuration. So device-patient interface can also be studied through post-mortem studies in order to understand better the biological response of these valves. For the interest of time, we're not going to talk about the detection of hazards and failure modes, but just importantly to say that when you look at a hazard or failure modes, there's 3 things you have to consider most importantly. That is the severity of the hazard or failure mode, the occurrence, whether there's a high probability or low probability to occur, and whether or not you can detect the failure mode or hazard mode. So who is the world's longest TAVI survivor? It's an 88-year-old female who was implanted 6 years ago with a Cribier-Edwards valve, and this figure was provided courtesy of Professor Cribier. And at that time, the aortic valve area was 1.68 centimeters squared with a mean gradient of 12. And the world's longest survivor with a core valve device is a 50-year-old female, was patient number 3, implanted in February 2005. This patient had a valve and valve. The 3-year follow-up was published in CCI. These were the images associated with the publication. And currently the patient's alive at 4 years and 8 months follow-up with normal valve function. So this is the last slide. And just to provide a framework on how new transcatheter valve designs may undergo testing. So we have to understand the loading conditions of the different valves. Every valve design is going to have different loading conditions. The heart leaflet, the Edwards, the core valve, they're all going to interact with the aorta differently. So we have to understand the loading conditions. These loading conditions are then imputed in the finite element analysis and in the testers. And we already went over how we calculate the factor of safety. Now these benchmark testers are then undergo regulatory review process. And if the FDA agrees, then we move to a first in man, and we can discuss what is a first in man. Do we need 20, 30, or 40 patients? And thereafter, this is where the crux of the problem comes in, is that now that we have in vivo data that we can understand through MSCT, fluoroscopy, and echocardiography, then we should go back to the beginning and understand that our presumed or assumed loading conditions match what the in vivo loading conditions are like. And this may improve valve durability, but more importantly, it may lead to patient safety. Thank you.
Niccolo, thank you very much for your very interesting presentation. Are there any questions from the floor? No. Okay. Yep.
So, given all these theoretical models that you presented, do you think that the valve durabilities will be different from a surgical valve implantation? So, all these different aspects that come with these percutaneous heart valves, they are very much different from surgical heart valves. Do you think that this generation will last as long as the surgical valves?
That's a tough question. I think we're only going to get the data as the time moves forward, but it may very well be that these valves may last 5, may last 10, may last 11 years. We're not sure. But we have to understand that the in vitro durability results do not necessarily equal the in vivo durability results if we don't understand the loading conditions that these valves are going to be applied to. So at the moment, in the acute follow-up period, there hasn't been any structural valve deteriorations of great frequency. But I think the proof in the pudding is going to be in the human experience, and we're going to have to follow that with time.
Okay, one very quick question, quick answer.
Apart from the degeneration of the material, I was thinking there is a lesson to learn from the aortic stents, and also it has been recently shown from the devices for closing ASDs and VSDs. Those devices move, maybe because the anatomy moves and they migrate. So is there any way to test the tendency of migration of those valves, because those are not fixed with sutures? So, apart from the degeneration of the leaflet themselves, is there any way to calculate if actually there is a movement upward or backward? Because this is an important issue. I think it's even more important maybe of leaflet degeneration.
I haven't seen of any reports of such, but you can imagine that maybe it's going to be an imaging modality for sure, whether it's echo or MSCT based. You're going to require some serial follow-up to compare to previously. But at this time, I guess we follow up the clinical